In this lesson, we're going to learn about cubic crystal structures and how cubic crystalline materials get their density. The unit cell is the smallest repeating unit of a crystal. Unit cells repeat in all three dimensions to build the macroscopic crystal. Lattice points are the points that define the structure of the unit cell. They can be atoms, ions, or molecules, depending on the type of crystal. In this lesson, we'll be looking at metallic crystals that have the same metal atom defining all of the lattice points of their unit cells. The lattice points are nuclei of metal atoms. Let's start with a simple cubic unit cell. A simple cubic unit cell has 8 atoms all in contact with each other, so its lattice points form 8 corners of a cube. We'd like to find the density of the material, which is its mass divided by its volume. Since density is an intensive property, the density of the material is usually about the same as the density of the unit cell. To approximate the density, we need the mass and the volume of the unit cell. The mass of the unit cell is the mass of the atoms that are actually within the unit cell. The unit cell is a cube with the atom's nuclei at its corners, so most of the space occupied by each corner atom is actually outside of the boundaries of the unit cell. Let's look at that more closely. In a cubic crystal made of many unit cells, a corner atom is shared by 8 unit cells. Only 1/8 of each corner atom is really inside the unit cell that we're weighing. A simple cubic unit cell contains 8 corners that contain 1/8 of an atom each, for a total of 1 atom per unit cell. To find the mass of the unit cell in grams, take the number of atoms in the unit cell, multiply by the atom's atomic mass, and divide by Avogadro's constant. Now that we have the mass of the unit cell, we're going to calculate its volume. The unit cell contains empty space, so you can't just calculate the volume of the atom from its radius. You have to use geometry to find the volume of the cube. All of the edges of the cube, A, are the same length. To find the volume of a cube, raise the length of its edge to the 3rd power, or cube it. We're going to find the edge lengths of a cubic unit cell as a function of the radius, r, of the atoms that make up the unit cell, because atomic radii are easy to look up. It's simple to find the edge length of a simple cubic unit cell because its edges contain its atoms' radii at all points. The edge of a simple cubic unit cell is 2 atomic radii long. The volume of a cube is its edge length cubed. To calculate the density, divide the mass in grams by the volume in cubic centimeters. Simple cubic unit cells aren't common in nature because atoms rarely stack right on top of each other. They settle into pockets like marbles settling in a jar. One of the more common unit cells for metallic crystals is called the face-centered cubic unit cell. A face-centered cubic unit cell has the 8 corners of a cube, but also has an atom in the center of each face. To find the mass of the unit cell, let's look at how many atoms it has. We've already established that a corner atom is shared by 8 unit cells, so it counts as 1/8 of an atom. 8 corners make 1 whole atom. Let's look more closely at the faces. There's an atom embedded in each face, shared by 2 unit cells. That means each of the cube's 6 faces contains half an atom, for 3 total. A face-centered cubic unit cell contains a total of 4 atoms. To find the mass of the unit cell, multiply 4 atoms per cell by the atomic mass, and divide by Avogadro's constant to find the mass of those 4 atoms in grams. Now let's find the volume of the unit cell. The first step is to find its edge length, A, which we're going to find as a function of the radius of its atoms, r. The atoms in the faces of the cube push their surrounding atoms outward, so the edges of the cube contain empty space. That's going to complicate finding the edge length as a function of the radius. We'll need to calculate the edge length as a function of atomic radius using Pythagorean geometry. We need a path between lattice points that passes through an atomic radius at all points, so it's a simple number of atomic radii long. For a face-centered cubic unit cell, that's the face diagonal, which is 4 atomic radii long. Remember the Pythagorean theorem. The length of the hypotenuse, which is the side opposite the 90-degree angle, is the sum of the squares of the lengths of the other sides. Using Pythagorean geometry, we can use the hypotenuse to solve for the edge length of the cube as a function of the radius of its atoms. For a face-centered cubic unit cell, the edge length is the square root of 8 times the radius of the atoms that make up the unit cell. Again, to find the volume of a cube, raise its edge length to the third power. Finally, divide the mass by the volume to calculate the density. Now we'll look at another common type of cubic unit cell, the body-centered cubic unit cell. It's still a cube with 8 corners, but it's called body-centered because it has an atom in the center of the cube pushing all of the corners outward. To find its mass, let's count its atoms. Again, it has 8 corners, each with 1/8 of an atom inside the unit cell for a total of 1 atom on the corners. The atom in the center is completely inside the unit cell, giving a body-centered cubic unit cell a total of 2 atoms. Multiply the 2 atoms by their atomic mass, and then divide by Avogadro's constant to find the mass of the 2 atoms in grams. Now let's find the volume of the unit cell again. We'll find a path between 2 lattice points that passes through an atomic radius at all points to derive the relationship between the cube's edge length A and the atomic radius R. In a body-centered cubic unit cell, the only path between 2 lattice points that passes entirely through atomic radii is the longest diagonal through the cube, and it's 4 radii long. We're going to need to use the Pythagorean theorem twice to find the relationship between the atomic radius and the edge length. Once to find the face diagonal B, which is one of the legs of the triangle that has the longest diagonal through the cube as a hypotenuse, and then to find the edge length A, which is one of the legs of the right triangle in terms of R. Our first use of the Pythagorean theorem shows us that the diagonal of a face is the square root of 2 times the edge length. Now we'll substitute the length of the hypotenuse, 4r, and the face diagonal in terms of A into the Pythagorean theorem to solve for A in terms of R. We find that for a body-centered cubic unit cell, the edge length is 4 times the atomic radius divided by the square root of 3. Now that we know how to calculate the mass and volume of unit cells using atomic mass and atomic radius, let's calculate the approximate density of a metal for practice. The precious metal rhodium is in the catalytic converters of cars. It helps to oxidize some of the pollutants that gasoline engines generate into other gases that are less harmful. Rhodium has an atomic mass of 102.9 grams per mole, an atomic radius of about 134 picometers, or 1.34 times 10 to the negative 8th centimeters, and it forms face-centered cubic crystals. Let's calculate its approximate density. We'll start by finding the mass of the unit cell. A face-centered cubic unit cell contains 4 atoms, and the mass of the cell is the mass of its atoms. We calculate the mass of 4 moles of rhodium atoms and divide by Avogadro's constant to find the mass of 4 atoms. Now we'll calculate the volume of the cubic unit cell, which is its edge length cubed. The edge length for a face-centered cubic unit cell is the square root of 8 times the atomic radius. Raise the edge length to the third power to get the volume of the unit cell. Now divide the mass of the unit cell by its volume to get the density of rhodium. The density comes out to be 12.6 grams per cubic centimeter. That's not far from the density of rhodium as measured in the laboratory, 12.4 grams per cubic centimeter.